This talk is part of the Noise Signal Finding Hemo Symposium. I'll be going over some basic concepts on the biophysical basis of fMRI noise that I hope you will find useful as background for the subsequent lectures in the symposium. Since the first demonstration in humans in 1992, fMRI has become the predominant approach for the non-invasive characterization of brain activity. Within a year of these initial studies, Weisskopf and colleagues pointed out in 1993 that noise-like components in the fMRI signal were partly due to physiological sources, in particular, strong fluctuations related to cardiac pulsations. Building upon that initial observation, the characterization of fMRI noise has greatly expanded and continues to this day as an active area of research. In this talk, I will review a number of key concepts that are important for understanding the mechanisms underlying fMRI noise. We will start by reviewing some basic characteristics of the bold signal. In fMRI studies, we are typically interested in variations in the bold signal referent to some baseline condition. Shown here in green, we have the baseline signal decaying with an effective transverse relaxation rate of R2 star B and measured at echo time TE. In the activation signal shown in red, the relaxation rate R2 star A has decreased, such that the signal at echo time TE has increased. If we look at the normalized change in the bold signal, we will find that to first order, it is the product of the echo time and the change in R2 star. In the next few slides, we'll take a closer look at the factors that contribute to R2 star. To understand R2 star in the context of fMRI, it's useful to recall that each hemoglobin molecule contains 4 heme groups, each of which has an iron atom. In the lungs, oxygen binds to these iron atoms, shielding them from the surrounding environment. In the brain, as oxygen is released to support cerebral metabolism, the iron atoms are exposed, and the resulting form is referred to as deoxyhemoglobin. The exposed iron atoms perturb the local magnetic environment, causing spins to precess at different frequencies and dephase over time. This dephasing leads to decay in the transverse MRI signal. As a result, the effective transverse relaxation rate is proportional to the total amount of deoxyhemoglobin. This in turn is proportional to cerebral blood volume and the concentration of deoxyhemoglobin raised to a power of approximately 1.5. The concentration of venous deoxyhemoglobin is given by the ratio of CMRO2, which is the cerebral metabolic rate of oxygen, and CBF, which is cerebral blood flow. An increase in CBF carries more oxygen to the capillary beds, and thus will tend to decrease the deoxyhemoglobin concentration. In contrast, an increase in CMRO2 means that more oxygen is being used by the brain, and therefore the deoxyhemoglobin concentration will increase. Putting all the elements together, we have that R2 star due to deoxyhemoglobin is proportional to cerebral blood volume, and the ratio of CMRO2 and CBF raised to the power beta. Although understanding is still incomplete, the current working picture is that changes in neuroactivity lead to changes in both CMRO2 and CBF. In addition, changes in CMRO2 may also trigger changes in CBF. Changes in CBF lead to changes in CBE, and the change in the total amount of deoxyhemoglobin depends on all 3 quantities. The resultant changes in R2 star then give rise to the bold signal change. Now that we've reviewed the factors that contribute to R2 star, we will take another look at the bold signal equation. In this first equation, we have the transverse relaxation term as before, but have added an initial transverse magnetization S0 of t and an additive background noise N of t. S0 of t represents the transverse magnetization that is present at t equals 0 before any relaxation has occurred. We can make a first-order approximation of the bold signal change in terms of the change in the magnetization term and the change in R2 star. Normalizing this by a baseline value gives rise to an expression that depends on time-varying changes in both a normalized magnetization term and a relaxation term that is proportional to delta R2 star. Now we will provide an overview of the factors that can give rise to noise-like fluctuations in both the magnetization and relaxation terms. Fluctuations in the magnetization term reflect temporal changes in measurements of the initial transverse magnetization at each location. This in turn reflects changes in local proton density and spin history effects, as well as susceptibility-induced distortions. Sources of variability include MRI system instabilities, subject motion, cardiac pulsations, respiratory activity, and inflow effects. On the other hand, fluctuations in the relaxation term reflect variations in R2 star and can thus be affected by factors that modulate CVV, CVF, and CMRO2. These include modulation of CVF by respiratory activity, modulation of CVV, CVF, and CMR2 by cardiac activity, and variability in all three quantities related to variations in blood pressure and intrinsic fluctuations in neural activity. Finally, note that the relaxation term exhibits a dependence on echo time TE, whereas the magnetization term does not. We will examine this further in the next slide. Here we take a closer look at the difference between the magnetization and relaxation terms. In this figure, all signals are plotted as a function of echo time TE. If we compare the magnetization-related signals in the baseline activation states, we see that the starting point changes, but the time constant of the exponential decay remains the same. As a result, the difference between the activation and baseline signals exhibits exponential decay with the same time constant. Normalizing this difference by the baseline signal leads to computing the ratio of two exponential decay curves with the same time constant. This ratio is independent of echo time. On the other hand, if we compare the relaxation-related signals in the baseline and activation states, we see that the starting point remains the same, but the time constant of exponential decay increases when moving from baseline to activation state. As a result, the difference between the activation and baseline states no longer exhibits a simple exponential decay, and the normalized difference is proportional to echo time TE. As we'll discuss in the next slide, this difference in the dependence on echo time affords us the opportunity to differentiate between the magnetization and relaxation terms. An integrated framework for differentiating the magnetization and relaxation terms was introduced by Kundu and colleagues in 2012. It is based on the acquisition of multi-echo EVI images. In this example, images are acquired at echo times of 15, 39, and 63 milliseconds, with the corresponding time courses shown in red, green, and blue, respectively, for a task-related fMRI signal from the visual area V1 shown in row B, and resting state fMRI signal from precunia shown in row C. The normalized changes in the signals from both ROIs exhibit a linear dependence on echo time, indicating that they represent bold-related relaxation terms. The processing model involves the first step of dimensionality reduction with PCA, followed by separation into independent components with ICA. The echo time dependence of the independent components is then examined. Components that exhibit a linear dependence on TE are classified as bold-like relaxation terms, whereas components that are relatively independent of TE are classified as non-bold magnetization terms. For components where the distinction based on echo time dependence alone is not clear, additional criteria are needed. In the following slides, we'll make use of this approach to help determine whether an fMRI noise source reflects changes in the magnetization term versus changes in the relaxation term. Subject motion is one of the primary sources of noise in fMRI time series. Although the use of image registration methods is a standard pre-processing step, it is long been observed that residual artifacts remain even after the application of image registration. These residual artifacts reflect limitations in the ability to rely on images, especially in the presence of large movements, spin history effects, and time-varying image distortion due to motion through inhomogeneous magnetic fields. These effects are expected to primarily manifest as changes in the magnetization term. The top row here shows the motion traces from a subject with relatively little motion on the left and one with a substantial motion on the right. Summary motion metrics, FD and DVARs, are shown in the second and third rows, where the vertical scales on the right span a much greater range to account for the increased motion. In the bottom row, the multi-echo ICA approach was used to compute the DVARs metrics associated with relaxation terms indicated as high kappa and magnetization terms indicated as low kappa. The magnetization terms show much greater agreement with the motion seen in the raw data, supporting our expectation that motion primarily affects the magnetization term. Multiband acquisitions are now a standard part of many fMRI protocols and offer higher temporal resolution as compared to single-band acquisitions. However, they may exhibit increased motion sensitivity due to the aggressive use of parallel imaging, as well as greater spin history effects with the shorter TRs that are used. These are some examples of multiband artifacts that were first identified with ICA applied to single-echo multiband EPI acquisitions. In later work, Olofsson and others used multi-echo multiband EPI acquisitions and the multi-echo ICA approach to show that these multiband artifacts primarily reflect perturbations of the magnetization term. Even a casual inspection of fMRI data quickly reveals the widespread presence of low-frequency drifts in the data. The nature of these drifts can vary considerably even between neighboring voxels. Although the mechanisms are not fully understood, potential sources include MRI system drifts, slowly varying displacement of the head, and low-frequency changes in physiology. Using the multi-echo ICA approach, Evans and colleagues were able to provide evidence suggesting that a significant portion of the low-frequency drifts can be attributed to changes in the non-bold magnetization term. However, Yan and colleagues have shown that the relative magnitude of drifts in the 0.0 to 0.01 Hz range exhibit a bold-like dependence on echo time. Thus, drifts most likely reflect effects on both the magnetization and relaxation terms. The identification of cardiac pulsation effects in fMRI dates back to the early work of Weisskopf and others in 1993. Later work demonstrated a clear relationship between fMRI signal intensity and cardiac phase, and showed that the effects were largely localized to large vessels, ventricles, sulci, and the edges of the brain. The induced signal changes are thought to reflect dynamic changes in the relative distribution of brain tissue, blood, and cerebrospinal fluid. In addition, there may be inflow effects, especially with short TR acquisitions. Taking these factors into account, we would expect that the effects should primarily affect the magnetization term. This is supported by a multi-echo IC example from Olofsson and others, showing a non-bold magnetization component that most likely reflects pulsations in the sagittal sinus. Another type of magnetization term artifact occurs from an interesting interaction between respiration and the EPI image acquisition process. When we breathe in and out, the volume of air in our thoracic cavity changes, and this causes time-varying perturbations of the magnetic field. These magnetic field changes lead to changes in the frequency of precession of spins in the brain. For an EPI acquisition, these frequency changes manifest as shifts in shading of the image that are most pronounced along the phase encode direction. In this figure from Raj and others, we can see that the center of mass of the image exhibits large fluctuations along the phase encode direction that occur at the respiratory frequency, whereas fluctuations along the readout direction are much smaller. Recently, it has been shown that respiratory-induced artifacts can lead to spurious increases in motion metrics, such as FD, that are commonly used to assess scan quality and guide image censoring approaches. Now I'd like to transition to factors that primarily affect the relaxation term. With variation in breathing, carbon dioxide levels can fluctuate considerably over the course of an fMRI scan. Wise and colleagues demonstrate that the fluctuations in end-tidal CO2 were strongly correlated with fluctuations in the bold signal across multiple brain regions. As carbon dioxide is a potent vasodilator, it's thought that fluctuations in CO2 lead to fluctuations in cerebral blood flow, which in turn modulate levels of deoxyhemoglobin and the bold signal. Thus, the observed changes are thought to act primarily through the relaxation term. Because of the additional equipment and setup that is required, most fMRI studies do not monitor end-tidal CO2 levels. However, it is fairly straightforward to monitor respiratory activity with equipment and software that is standard on most MRI systems. Using a measure of respiratory activity referred to as respiration volume per time, or RVT, Byrne and colleagues found that the depth of inspiration, indicated here by the blue envelope, was related to fluctuations in the bold signal. The fluctuations are considerably reduced when the subject is asked to maintain a relatively constant depth of inspiration. In subsequent work, Byrne and others went on to demonstrate that the fit between RVT and the bold signal is greatly improved when the RVT signal is convolved with the respiration response function, which is obtained as the average response to a single deep breath. Chang and Glover later demonstrated that the filtered RVT signal is strongly coordinated with measures of end-tidal CO2, indicating that a significant portion of the respiratory effect is mediated through its effects on CO2. In addition, other mechanisms reflecting respiration-related change in thoracic pressure and baroreceptor regulation may also modulate CBF and give rise to changes in the bold signal. Up to now, we have focused on a picture in which respiratory-related changes are considered to be the primary driver of the associated bold signal changes. However, a study by Yuan and others suggests that additional explanations may need to be considered. In this study, the authors used simultaneous EG-fMRI measures to assess the dynamic relationship between global field power, referred to as GFP, RVT, and bold fluctuations. They found that GFP and RVT were significantly correlated, and that the changes in GFP led to changes in RVT. Time-lag versions of GFP and RVT were both correlated with the bold signal across multiple brain regions. Interestingly, the authors found that the effects were significant when the subjects had their eyes closed, but not when the subjects had their eyes open. These findings suggest that under some conditions, fluctuations thought to be due to respiratory activity may actually reflect underlying neuronal activity that drives both respiratory activity and bold signal fluctuations. The need to reconsider the neuronal causes of artifacts is also pointed out in a study by Zhang and others, where they compared a group of subjects who exhibited low average motion to a group with high average motion. After censoring time points such that both groups exhibited the same average levels of motion, they found that the high motion group exhibited greater functional connectivity between nodes of the default mode network. In contrast, there was no difference in functional connectivity when comparing data from low motion and high motion sessions of subjects scanned twice on separate days. These findings suggest that there may be neuronal precursors to motion that may be obscured when motion-related bold signal changes are simply considered to be confounds. A phenomenon that is receiving increased attention is the presence of globally coordinated activity across the brain. This can be readily observed in fMRI data, as shown by the dynamic and spatially widespread positive and negative signal levels seen in these images of a single slice of fMRI data across 45 time points. Similar phenomenon can be observed using other modalities, such as this example obtained with optical imaging of neuronal calcium signals in a transgenic mouse model. In fMRI, global activity is often summarized with what is referred to as the global signal, which is computed as the mean of all the signals in the brain. It has been shown that this global signal is highly correlated with the bold signals measured in the large draining veins, as well as measures of peripheral oxygenation obtained from the fingertip. Of particular relevance to this symposium, the timing lag structure of the global signal exhibits a high degree of spatial structure. For the most part, the global signal has been treated as a confound, especially in resting state fMRI studies, and is regressed out using a procedure known as global signal regression prior to the computation of functional connectivity maps. The presence of the global signal can often obscure the underlying information in functional connectivity maps obtained with minimal preprocessing, and the application of the global signal regression has shown to be very effective for revealing the underlying connectivity structure. However, the use of global signal regression is controversial, as it has the potential to introduce negative correlations. In addition, there's growing evidence that suggests that the global signal contains useful information. For example, simultaneous EG-fMRI studies have shown that the global signal is negatively correlated with the EEG measures of vigilance. Global activity tends to be high when vigilance is low, and tends to be low when vigilance is high. Thus, pre-processing methods such as global signal regression may be removing the effects of vigilance fluctuations from the data. In this talk, we've considered a number of sources of noise in fMRI. We've reviewed how the fMRI signal can be viewed as a sum of a magnetization term and a relaxation term. Potential sources can modulate one or both of these terms. For example, respiratory activity affects the magnetization term by perturbation of the magnetic field, and may affect the relaxation term through a number of physiological mechanisms, including modulation of carbon dioxide levels. While it's common to treat the effects of potential noise sources as confounds in analysis of fMRI data, there is a growing appreciation that many of the noise-like signals that have traditionally been treated as confounds may, in fact, carry useful information. The challenge in distinguishing information of interest from noise stems from the fact that many noise sources, such as motion, respiration, and cardiac activity, ultimately have their origins in the brain networks that control these functions. Minimizing the contributions of potential noise sources therefore risks removing potentially useful information about brain activity. As fMRI continues to evolve, it will be important for the field to remain mindful of this issue and develop new analysis approaches that more effectively consider the integrated nature of signal and noise in fMRI. Thank you for your attention, and enjoy the rest of the symposium.